Hello students, today I am going to discuss hyperconjugation. In my previous video, I have discussed resonance where only pi electrons are involved in resonance. So in resonance, we have seen that only pi electrons are involved. So now I am going to discuss another type of resonance that is called hyperconjugation. This is hyperconjugation. So what is the difference between hyperconjugation and resonance? I am going to discuss. In resonance, we have seen that it involves pi electrons, but in hyperconjugation, it involves actually sigma electrons. Sigma electrons are involved in hyperconjugation. So it involves delocalization of sigma electrons. It is better to say delocalization of sigma electrons. So now obviously one question arrives in your mind, that is when hyperconjugation will take place. Suppose hyperconjugation will take place when a saturated carbon containing CH bonds. See, this is saturated carbon. This is saturated carbon. It contains CH bonds. Now this saturated carbon is attached to another unsaturated system that possesses either a vacant or half-filled p or pi orbital. So this is unsaturated carbon. I am marking by red color. So this is unsaturated carbon. Okay. So now it can be either vacant or half filled. When it is vacant, so it is obviously positive charge, or when it is singly occupied, then it is obviously free radical. So this is the skeleton of hyperconjugation. This system should be present in in the molecule where hyperconjugation is possible. I think it is clear. Now I am going to write a proper definition. So it says that hyperconjugation is a type of resonance where the electrons of a CH bond of a saturated carbon atom is delocalized into either a vacant or half-filled p orbital or a vacant pi orbital of an adjacent unsaturated system. So that's a carbocation, like where a saturated carbon containing CH bond is attached to the positively charged carbon that has a vacant p orbital. So this is this type of system. So this is saturated. This is saturated carbon. Now this is attached to an unsaturated system containing a p orbital. So it is vacant. That is why I am putting a positive charge on this in this p orbital. Now we can have this type of sigma electron delocalization. So this CH bond contains 2 electrons. Now we know any bond formation requires 2 electrons, and here there will be new pi bond, and this pi bond will be formed is formed by this sigma electrons pair. Now it will be H plus. Okay, this is very simple. So sigma electron gets delocalized and it forms a pi bond, and H plus is situated near by this pi cloud. Now from this point of view, we can say that hyperconjugation can be said as no bond resonance. No bond resonance. Clear? Here this hydrogen atom is not, it is not free. It is not free. And the effect is to increase the ionic character of the CH bond. So higher the ionic character of CH bond, higher will be the probability of hyperconjugation, you can say. So now, because here I'm trying to say that the electrons which becomes partially delocalized through conjugation. So orbital picture will be like something like this. This is sigma bond, sigma CH bond. This is vacant p orbital. Now it contains 2 electrons. This sigma CH sigma bond. Now this CH sigma electron pair gets delocalized to this pi system. It forms a this pi bond. Now this type of overlap, what is the benefit of this overlap? It helps to delocalize the sigma electrons, and we know, and the if number of and this hydrogen is called hyperconjugative hydrogen, and if number of hyperconjugative hydrogen increases, then probability of delocalization of sigma electrons will also increase. So and also we know that higher the delocalization, higher will be the stability, so it gives molecular stability. So hyperconjugation gives molecular stability, just like resonance. Clear? Now I am going to show this orbital diagram through a real molecular model kit. Let's see. This black ball represent sp3 carbon. See, we have 3 CH bonds. Now this sp3 carbon, it is attached to a carbocation. Hybridization of carbocation is sp2. We know sp2 has one vacant p orbital, so this is vacant p orbital, and these are the 2 hydrogen attached to this sp2 carbon. Now see, this vacant p orbital and this CH bond, these CH bonds are in a same plane. So we can expect a CH pi conjugation, so that is hyperconjugation. And now as it is sp3 carbon, so it can rotate. Now this hydrogen is now is now in the same plane of this p orbital. So again we can expect a CH pi interaction, CH orbital conjugation. Then again this CH bonds can it can also rotate. Now again it is in the same plane of this p orbital, so again we can expect a CH p orbital conjugation, so that is hyperconjugation. So in this model we are expecting 3 hyperconjugative hydrogen, 1 2 3. So both, because these all these 3 hydrogen can come in the same plane of this vacant p orbital. So we have CH bond contains 2 electrons, and these 2 electrons will be used to form a new pi bonding formed by CH and vacant p orbital. As I just few minutes before I have told you that higher the number of hyperconjugative hydrogen, higher will be the stability. So let us discuss the stability of carbocation. Like we know this is what is the 3-degree carbocation? Just I am going to write, I am going to draw the 3-degree carbocation. So this is vacant p orbital. So number of hyperconjugatives, number of hyperconjugate hydrogens are here 9, 3, 6, 7, 8, 9. So these are all hyperconjugative hydrogen. So obviously in 3-degree carbocation number of hyperconjugative hydrogen is 9. Two-degree carbocation. Now I am going to draw the 2-degree carbocation. So according to the definition, this is unsaturated carbon, and this unsaturated carbon contains vacant p orbital, and it is attached to 2 saturated carbon containing sigma CH bonds. So number of hyperconjugative hydrogen will be 6, 3 here 3, so total 6. Now in 1-degree carbocation, so in 1-degree carbocation it is clear that number of hyperconjugative hydrogen is only 3. What is in primary carbocation? This is primary carbocation. This is, so this p orbital, this unsaturated, it is unsaturated carbon, it contains a p orbital, like there is no other saturated carbon attached to this carbon, so 0 hyperconjugative hydrogen. Clear? So as I told you that higher the number of hyperconjugative hydrogen, higher will be the stability. So obviously stability order will be this one. Clear? So 3-degree greater than 2-degree greater than 1-degree greater than primary carbocation, so higher stability will be 3-degree carbocation, and the same conclusion can be drawn from plus I effect. Plus I effect also says similar same thing. Okay, now we are going to see what happens in free radical system. So a free radical in which a saturated carbon containing CH bond is attached to, so this is saturated carbon, it contains a CH bonds, and it is attached to another, it is attached to a unsaturated carbon containing a p orbital, and here this p orbital contains only 1 electron. Now obviously we know that like each bond requires 2 electrons. Here this is CH bond, it has 2 electrons, so out of 2 electron, 1 electron will be used to form a pi bond, because 1 electron here, 1 electron will be coming from this CH bonds, and remaining electron will be coming from this p orbital. Clear? This is actually half filled p orbital. It means it contains only 1 electron. So this will be the result. Conjugation, sigma electrons conjugation. New pi bond, and here will be H dot, because out of its CH bond contains 2 electrons, 1 electron just is required, because already in p orbital there is 1 electron. Clear? So this type of hyperconjugation we are expecting in free radical system. So similar in this similar way in TARS 3-degree free radical. In 3-degree free radical, how many hyperconjugative hydrogens are present? Answer is 9. Let's see. So 3, 6, 9. Clear? So 9 hyperconjugative hydrogen. Here 3, 6 hyperconjugative hydrogen in 2-degree free radical. In 1-degree free radical, only 3 hyperconjugative hydrogen. So in primary free radical, 0 hyperconjugative hydrogens. Clear? So obviously we know that higher the number of hyperconjugative hydrogen, higher will be the stability. So stability order will be 3-degree means tertiary, then 2-degree means second, then 1-degree, then primary free radical. Stability order. Clear? Now just go back to this definition. Here I told you vacant or half filled p orbital or a vacant pi orbital of an adjacent unsaturated system. Now I am going to consider this one. So an alkene is also stabilized through hyperconjugation involving the following canonical forms. How? So this is suppose this is double bond, this is saturated carbon, it contains CH bonds. Now these CH bonds can involve these CH sigma electrons involves in hyperconjugation. But how? Let's see. Then this is the new pi bond. So if I show you the arrow notation, but it is not appropriate here, but just for understanding I am telling you. Just for understanding, I should not show you in this way. Just for understanding purpose, I am showing this arrow notation. So this two sigma electrons in CH bonds forms pi bond here, and now this pi bond breaks. This pi bond breaks. Now this pi electron will be here, and here will be H plus. So as well molecule is neutral. See, this is neutral molecule, and obviously the canonical forms will be also neutral one. Okay, clear. Now it will be clear from orbital picture. Now I am going to show you the orbital picture. Now these two sigma electrons in these CH bonds, this is hydrogen. Now we are expecting interaction, this interaction with this p orbital. Now if when these sigma electrons two sigma electrons interact with this p orbital, then obviously this interaction will be broken down, will be broken. So that is how these two electrons will now will now will be here. These two pi electrons, these two pi electrons get shifted to this p orbital. It is clear. So that is how I have put a negative charge on this carbon, and this I have put a negative charge on this carbon. I think it is clear now. So obviously increase in hyperconjugative hydrogen means higher the number of hyperconjugative hydrogen, higher will be the stability of alkene. Let's see. So this is I am drawing a simple alkene. This is one butene. Here number of hyperconjugative hydrogen is only 2. Only 2 hyperconjugative hydrogen. Here number of hyperconjugative hydrogen is 6. Six hyperconjugative hydrogens. So obviously both contains 4 carbon. So but as it has 6 hyperconjugative hydrogen, where it has only 2 hyperconjugative hydrogen, so this one will be more stable than this stability order. So this type of question will come. So you need to you need to write the correct order of stability using hyperconjugation, using this concept, where you need to count the number of hyperconjugative hydrogen. I think you get the point. You are getting the point. Clear? So for today I am going to end my lecture. So see you next videos. Okay, bye.